Same problem. And this will be the last entry. Okay, so is the screen now visible? Is the screen visible now? Okay. So today is the second lecture of the course Molecular Spectroscopy of your third semester. So in the first lecture, we discussed about the various kinds of electromagnetic radiations and waves and all backgrounds related to the electronic spectroscopy and its development of quantum mechanics and understanding various concepts of quantum mechanics to understand the electronic energy levels of atoms. So, and all of you have already learned a lot of information regarding the structure of atoms and structure of molecules in your previous courses, and you all have idea about the electronic structures which we found that are discrete in nature, that we have found from both theory and little bit corrections over there. And then we have learned about various impact of electric and magnetic fields, that is like Stark effect and Zeeman effect on the atomic energy levels. But what about the energy of the intermolecule? That is a question. So whether this is quite different or it behaves different ways like electronic energies or anything else. So as you know, in last time I talked that the molecules may have three kinds of energy. If we for simplicity, if we talk about only simply a diatomic molecule, suppose hydrogen H2 or nitrogen N2, there are two atoms, hydrogen, one hydrogen is there, two hydrogen atoms are there, and they are connected by a covalent bond. And now these atoms may have rotational energy, it can rotate about a certain axis. So that rotation leads to have some energy of the molecules. That is known as the rotational energy. The atoms may vibrate. As you know, the atomic positions are not actually fixed. They actually vibrate about their mean position. So they possess some vibrational energy also. And third one is obviously the electronic energies. So these are the three types of energies possessed by molecules: rotational energy, vibrational energy, and electronic energy. But not all the atoms have all these three components. That I will be discussed, that which type of molecules have which type of components. That is either rotational or vibrational. Okay, so that will be decided by the structure of the molecules and type of molecules, whether this is polar or non-polar like that. So before discussing in detail, we shall discuss about the structure of molecules. In today's lecture, we shall mostly focus on the rotational spectrum of the molecules. That means the energy levels of the molecules owing to the rotational motion of the molecules themselves, right? So before going into that, let us look into the structure of molecules and their classifications. So as you have mentioned, we are talking about the rotation. So rotation may occur with reference to a particular plane, with reference to a particular axis, right, or about a particular point. We shall mainly focus here the rotation of the molecules about some axis. Okay, so various type of axes are possible, and depending on that, we classify the molecules in different categories. Right. So here you see this is a diatomic molecule. So this is a hydrogen molecule. This is one hydrogen atom, and this is another hydrogen atom, and this is the covalent bond. These molecules have one axis like this, that is along passing through the bond actually. So that we term as A axis. Another axis which is directly perpendicular to this bond and which lies in the plane of the screen. Okay, so this is second axis. This is termed as the B axis, and the third one which is perpendicular to both these two axes. That means here this which is termed as C. This axis is perpendicular to this screen. Okay, so these are the three different axes, and the principal moment of inertia about these three axes are denoted by IA, IB, and IC respectively. Okay, now this IA, IB, and IC, all these three quantities may be equal, maybe any two of them are equal, or all of them may be unequal. And depending on that, and depending on the atomic arrangement, we have the following classification of molecules. The first one is the linear molecule. So as the name suggests, and as you can see in the picture, the linear molecules means the atoms of the molecules are arranged linearly. That means the bonds are basically linear. Here we have the this is I think CH2 like that. So what we have, this is a linear molecule, and in this case you see, if we consider these axes, as you have told, the axis passing through the bond, that is A axis, if we consider these axes, and as all the masses of the molecules are contained on these axes, so the moment of inertia about this axis, if the molecule rotates about this axis this way, its moment of inertia will be obviously zero, as you have already done in your mechanics course. So for any linear molecule, if you say this IA equal to 0, and since this is a symmetric type molecules, this IB and IC will be equal. So this is the case of linear molecule, and the examples are HCl, OCS, HCN, C2H2, and CO2, etc. Right. Second kind of molecule we talk about is called the symmetric top molecules. As the name suggests, the symmetric top molecules with two rotational axes that have same inertia and one unique rotational axis with a different inertia. Now let us explain like that. So this is the symmetric top molecules, where we have these three atoms are like this, and here another atom, and this is actually carbon. These three are hydrogen, and this one is chlorine. This is basically CH3Cl. Okay, so this is the A axis, and other two axes are B axis and perpendicular to the C axis. And where now in this case you see the bonds are aligned along different axes. So earlier what we have shown that the axis passing through the bond will be axis, that definitions will not be applicable over here. So what we take, that it has, you see, it has a threefold symmetry about this axis, right? We have this molecule. If you rotate about this axis by threefold, I mean, so 120 degrees, then in each case you have the same structure. So it has threefold rotational axis. So that's why this axis is termed as the A axis, right? And this will be B axis, and this will be C axis. Okay. These IA, IB, ICs are the moment of inertia of this of the atom with respect to these three axes. Now, if you take the moment of inertia about this A axis, that will be completely will be different from this B axis and C axis respectively, right? So there are several possibilities. If the structure is like that, that IB equal to IC, this IB and ICs are equal but greater than IA, in that case, that is called the prolate. Molecular shape is called prolate. And most common examples are CH3Cl, CH3F, CH3Cn, NH3, etc. These are basically the prolet structure molecules, symmetric top molecules. Another kind of structure that you can observe usually in case of BF3 and BCl3, that is oblates type of structure. In this case, this Ia equal to Ib, but that is less than Ic. Okay, these two are A axis, B axis, and this is C axis here. So this Ia and Ib are equal but not equal to Ic. As you can already see, the mass distribution are different. Those are called oblate molecules. Okay, so that is called oblate symmetric top, and this is called folded symmetric top. And these are the examples that you see. The third one, actually, this should be third one, that is spherical top molecules. So, what are spherical top molecules? As the name suggests, that the molecule is symmetric about the origin, about a point. So, here, if you see, this is CH4 molecules. This is the carbon atom. These are 4 hydrogen atom, and this molecule is symmetric about this carbon atom. And all the moment of inertia, principal moment of inertia, Ia, Ib, and Ic are all equal. Okay, so that is why this is called spherically top molecules. And here, this Ia and Ib and Ic, wherever we say, this represents the principal moment of inertia. And all of you know what is principal moment of inertia. And next onwards, whenever we say this is the moment of inertia, it always represents the principal moment of inertia. Okay. And the example of spherical top molecules are CH4 that I have already shown here, and others are SF6, CCl4, etc. And you can find any general chemistry book, or you can just Google it to get this symmetric structure of these molecules also. And another one is asymmetrical top molecules. And as the name suggests, that these are the molecules for which this Ia and Ib and Ic are, all three are different. Okay, all these three principal moments of inertia are different, as if the structure is asymmetric. You know, the structure is asymmetric means the moment of inertia about those axes will also be will also not be equal. And the common examples are H2O, CH3OH, CH2Cl, etc. And I was quite surprised when I just Google that asymmetric top, and what I find, the result is like this. So these are basically what I find. These are nothing but dresses for girls. And if you see, these dresses are basically asymmetric, and that's why the name asymmetrical top. I don't know what is this, but Google showing this, and we find a very relevant relation between these asymmetrical top molecules and asymmetrical top dresses, all are things. So anyway, these are the various type of molecules that we have learned, and these molecular structure has an important role in determining whether these molecules will show the rotational spectra or not. And that will be discussed in the foregoing sections, that which molecules will show rotational spectra, what are the criteria for that, that we will see. So let us understand the interaction of rotation of molecules with electromagnetic radiation. So when an electromagnetic radiation is incident on a rotating molecules, how the molecules responds to the electromagnetic radiation, how the molecule interact with the electromagnetic radiation, right? So for this purpose, we consider a diatomic molecule having a dipole moment along this way. You see, this is the delta plus charge, and this is delta minus charge. If you consider about, say, HCl molecule, we have delta plus charge over H atom and delta minus charge over Cl minus 1. So that leads to a creation of dipole moment from hydrogen to chlorine atom itself. So let us consider, suppose this is an HCl molecule, a simple diatomic molecule. So this is the delta plus charge, this is delta minus charge, and the dipole is directed along this direction. Okay. So when the molecule rotates about an axis, suppose it's rotating about an axis perpendicular to this this slide, this screen. about the screen, it's rotating. Okay, so it's rotate and clockwise. So now it has comes into this position. So when this molecule rotate about this axis perpendicular to the bond, obviously the direction of the dipole moment will change. Earlier it was this way, now this will be along downwards. Okay, and this continuous rotation of the molecule leads to a continuous change in the direction of the dipole moment. And as a result, we have shown a periodical vibration of the direction, change of direction of the dipole moment of the molecule. And this change will generate a fluctuating electric field. Okay, and this electric field will now interact with the incident electromagnetic radiation or incident electromagnetic field applied on the molecule. So if the molecule have zero permanent dipole moment, suppose if the molecule do not possess any permanent dipole moment, then obviously this change will not affect any kind of dipole moment like that, because this permanent dipole moment is zero. So the electromagnetic radiation will not interact with the molecule. But if the molecule possesses some dipole moment, obviously the interaction will occur. So this is the most important issue in observing the rotational spectra, because if the molecule do not have any permanent dipole moment, it will not interact with the electromagnetic radiation during rotation. So this molecule will not exhibit any kind of rotational spectra. So as a tagline, we have all the molecules which do not have any permanent dipole moment will not interact with external electromagnetic radiation and doesn't exhibit any kind of rotational spectrum. So if you consider about the homonuclear molecules like hydrogen, H2, nitrogen, oxygen, etc., these are usually spherical atom molecules and they do not have permanent dipole moment, and they will not show any rotational spectrum. Similar other examples are obviously CO2, CS2, etc. Even isotopic substitution does not produce any activity. Suppose in case of CO2, we can take carbon 12 or carbon 13, but that will not affect its rotational activity or interaction with the electromagnetic radiation, because its rotation does not lead to change of any kind of dipole moment that will interact with the external radiation. Okay. So the transitional dipole, if we do a little bit of quantum mechanics, then we can find that if the molecule have a transition from this ith state to jth state, and this psi I and psi j represents the wave function of ith state and jth state, then the transitional moment mu ij will be given by psi I star mu psi j d term. That means that they have this psi I, psi j are basically the ith and jth rotational state over the entire volume d term. And simply this psi n and psi I and psi j are nothing but the spherical harmonics that we can solve from Schrodinger equation. And based on this general angular momentum theory, the angular momentum quantum number L that we have already designated in atomic physics, now it is redesignated as this capital J. The angular momentum will now be designated by capital J. And the fitness of transition moment will have some selection rule. I'm not going into derive all the selection rules, but we just you have to remember these two selection rules. First, the molecule must have permanent dipole moment, and the second, the transitions are allowed only between the adjacent rotational levels. That means delta J will be either +1 when the molecule absorb energy and -1 when the molecule emit energy. So these are the two important selection rules that you have to remember. And this is the first one, obviously the criteria for a molecule to exhibit the rotational spectrum. right? So now let us discuss about the rotational spectra of a rigid diatomic molecule. Okay, so here you see this is a diatomic molecule of two different atoms. Suppose this is an HCl atom. So this is one is hydrogen atom, this is chlorine atom, and they are connected by this is one is the bond, the covalent bond they have, and this is the center of mass. And this is R1 and R2. And let the molecule rotate about an axis perpendicular to the bond axis. That means this is either B axis or C axis. And this about this A axis, this its moment of inertia is 0, obviously. And about this axis, this is the center of mass and the axis passing through the center of mass, and the bond length is R. And from the center of mass, this H molecule is at, or mass M1 is at a distance R1, and the atom mass 2 is at a distance R. And we do a little bit of quantum mechanics to get the energy. And in fact, from the classical data, you can also have the energy. The rotation energy of this system will be equal to how much? Ej equal to h cross square. In classical mechanics we have learned. What will be that? K square. Wait a minute. That is actually for general wave. That is not the rotational energy. So what is the rotational energy of a molecule in classical mechanics? This is half I omega square, right? This is half I omega square. Again, I into omega is L, angular momentum, that is L square by 2I. Or here we have term, we use the angular momentum as J, so that will be J square by 2I. And if we use the Schrodinger equation, the J square, the eigenvalue of J square will be replaced by J into J plus 1 H cross square. So this is the energy Ej equal to H cross square J into J plus 1 by twice I. So this is in joules, suppose. And this J takes values, integral values 0, 1, 2, 3, and so on. Now, we can calculate the internal moment of inertia of this molecule about this axis. This will be I into M1 R1 square plus M2 R2 square. And obviously, moment of mass about this center of mass will be same. We have, so M1 R1 will be equal to M2 R2. And we already have R equal to R1 plus R. So this is a simple classical calculation that you can do. And if you take any of this value over this equation, you can find R1 and R2. So this is the value of R1 and this is the value of R2 in terms of this R, the bond length. And then you can find from this equation, you can find I equal to M1 M2 by M1 plus M2 into R square. That is mu into R square. So this mu is M1 M2 by M1 plus M2 is known as the reduced mass of the system. Okay. So however, in molecular spectroscopy, it is very convenient to express the energy in terms of wave number, right? Wave number means 1 by lambda, number of waves per unit length. So what will be that? 1 by lambda, that is E by Hc, and that is termed as epsilon j. So this epsilon j equal to Ej by Hc. So we already have this Ej, so we have to just divide by Hc. So H by H by square Ic j into j plus 1. And it is usually expressed in the unit centimeter inverse. Okay, obviously it should be the length inverse because this is 1 by lambda, but the conventional unit in molecular spectra to express this wave number in centimeter inverse. So now take this H by H by square Ic as B. So this Ej will be B into j plus 1. They obviously starts from 0, 1, 2, 3, etc. B, H by 8 pi square Ic, this is known as the rotational constant of the molecule and it depends on the moment of inertia. Okay. Now, if I'll show the molecular levels before going. Suppose if a molecule is in a state J double dash and it is excited to another state J dash. Okay. So the energy difference between the two states will be E J dash minus E J double dash. So for E J dash, the energy will be B from this equation B J dash into J dash plus 1 minus for this E J double dash, it will be B J double dash to J double dash plus 1. Okay. So this is the energy difference between the two adjacent states. And as we have already mentioned, the selection rule is delta J equal to plus minus 1. If you consider the absorption, then that means the molecule is transitioning from lower energy state Z dash to the upper energy state Z, from lower energy state Z double dash to the upper energy state Z dash, then delta J will be +1 when Z dash minus Z double dash equal to 1. So if we put this Z dash minus Z double dash equal to 1, we have this relation. That means this now this epsilon J bar is actually written as nu J bar, that will be 2b into J plus 1 with J equal to 0, 1, 2, 3, etc. Now, so this is the mathematics that we have done to get the expression for the energies. Now, what is the how the energy levels look like? So this is actually the energy spectrum. We can just put these values. If we put J equal to 0, E1, E0 equal to 0. If we put J equal to 1, then EJ equal to 2B. If we put J equal to 2, this will be 6B and so on. So here you see, this is J equal to 0. These are the J values. J equal to 0 corresponds to energy 0. J equal to 1 corresponds to energy 2B. J equal to 2 corresponds to 6B and so on. And as you can see, on increasing the J values, the energy gap between the adjacent molecular energy rotational levels also increases. So, and as I already mentioned, the selection rule is delta J equal to either +1 or -1. If we take the absorption, that means from lower levels to higher level transitions. So delta J equal to +1. So if a molecule starts from here to here, this gap is got 2B, so nu bar equal to 2. It can start from here to here, 1 to 2, that will be 6B minus 2B, that is 4B. It may jump from 2 to 3, so the energy gap, that means nu bar will be 12B minus 6B, that is 6B, and so on. So this will be 0, 2B, 4B, 6B, and 8B. And the separation you see, this is same. The energy gap is increasing, but the line separation between the levels, the absorption spectrum is same. So here is an experimental data. I think the scales are not properly visible. This is the wave number in centimeter inverse, and this is the transmission in percentage. So you see, these are the various absorption lines. Okay, these are these 0, 2B, 4B, 6B like that, and you see these are equally spaced almost. But one feature that you can see clearly that these absorption bands do not have the same intensity. Okay, these they do not have the same intensity. So the intensity of the absorption bands are different. That will be discussed a little bit later. So now we shall discuss about the effect of isotope on the rotational spectrum. Suppose we have a molecule which corresponds to have this energy, this EJ or nu bar, what do you say, this 2BG into J plus 1. Suppose this is an HCl molecule, okay, and the hydrogen is 1H1 and the chlorine is 17Cl35. Now, if the HCl molecule have H1H1, hydrogen is 1H1 and chlorine is 17Cl37, the another isotope of the molecule, what will be changing? Because where you have in the energy expression we have 2B, and this B is connected to the moment of inertia, and the moment of inertia is connected to the mass of the system. So if we take this is as the Cl molecule, for Cl35 this M2, and for Cl37 this M will be different. So mu will be different, I will be different, and this B will be different. So this energy spectrum will have a change. So if we take the new value as B dash instead of B, suppose for the molecule say HCl, when Cl equal to 35, the rotational spectrum has wave number nu bar, that will be twice B into J plus 1, and for HCl for when Cl is substituted by Cl37, this is 2B dash into J plus 1. So the equation will be this, the shift in the frequency. And if we take a common of these, and if we take these B values, H by 8 pi square IC, and we have I over here, then we have this kind of expression. And here this we have used this rho as the ratio of this molecule. I think this I should not be here. Okay, this I should not be here because I is already over here. Oh no, I is taken. No, I should be here. Okay, it's okay. And this is the expression. And I by I dash is basically rho square. That is the ratio of the moment of inertia of the molecule and its isotope. So you see, if we change the isotope, here I am showing the result for carbon monoxide. When for this one for carbon 12 and this one for carbon 13, as the mass increases, if you see, as the mass increases, the moment of inertia increases and this B value decreases. So this energy levels will be shifted downwards. So for the new spectrum, the energy bands will be shifted towards lower wave number. That is, will be shifted like this. It will be shifted like this way. I think we I'll show another example later where you can see this observation. Okay. Now that I have mentioned from this spectrum that all these spectrum have different intensities. So can any one of you please tell me why these intensities are different? Any idea? Any other options? Why the intensity of these rotational bands are different? No, these are only we are considering the rotational energy levels of the atom as a whole. Okay, not the electrons. These are rotational energy levels of the entire atom, not atom, entire molecule. Okay, let's see why these intensities are different. Because you first of all, how the intensities comes from? It comes from the transition of the atoms from higher energy state to lower energy state. This is what we do. So if the number of molecules in the different states becomes different, obviously these transitions will be different. And as we know, the population depends on the energy, and that is given by this Boltzmann distribution, n equal to n0 to the power minus ej by kt. Right? This is a common general Boltzmann distribution, you know. And this ej we have already got this one. This ej equal to h by 8 pi square ic, and this ej equal to this small ej equal to bj into j plus 1. So capital ej will be called hc into ej. So bj hc into this one. So that's why I have written the equation like this. Is bhc j into j plus 1 by kt. And another thing is there. There is the degeneracy of the levels, because since this is the angular momenta, for each j values there are 2j plus 1 rotation probability, right? The 2j plus 1 orientations of angular momenta vector. So higher the degeneracy, higher will be the probability of molecular occupancy. So it is also proportional to the degree of degeneracy of the states. So the number of populations, that means number of molecules in a state, is equal to some n0 into the degeneracy 2j plus 1 into the Boltzmann temperature, Boltzmann energy temperature factor, it will be power minus ej by kt. And if we show a plot with this j versus this entire term, we are plotting this. This is at n0 by nj. So this, it will start from 1. It will go on increasing and decrease like this. If we increase the temperature, the situation will be this. Because at higher energies, more and more molecules will be excited to higher energy levels, right? So the peak will be shifted to this way, and intensity will be high. So for if we consider this temperature, for this temperature 300 Kelvin, so this is the J values for which the population is maximum. So how to calculate these J values? We shall just differentiate this. You can also just take it as homework. You just differentiate this with respect to J and find the J values. it will comes like this. So this is the J value which corresponds to the maximum population. That these J values will contain the maximum number of molecules. Okay. So now this is the idealistic case. But in practice, the rotator is not a rigid one, because the bond is not like that. This is a rod-like structure and its length is not changing, but rather the molecule actually vibrates about the bond, about the mean position. So during rotation, there are centrifugal forces. So the bond length actually not fixed. That means we cannot say the diatomic molecule as a rigid rotator, but rather it is a non-rigid type. So if this is non-rigid, centrifugal forces will be there, and the centrifugal forces will be proportional to the angular momentum square. You can just do some little bit of classical mechanics. The centrifugal force is how much? Minus m omega square r. Okay, and if you replace J equal to I omega, and you will get this one, that is the force, and force multiplied by the length, that will give you the energy, and you will get this expression exactly. So the energy will be this. This is the actual for rigid rotator, and due to the centrifugal distortion, this amount of energy will be lost. So now the new energy will be this Bj into J plus 1 minus D J square into J plus 1 also. And this D, we have just assumed this one as the centrifugal distortion constant. And we have assumed as nu bar is equal to this nu by C, that is 1 by 2 pi c root k by mu, the general frequency of vibration of the bonds. Okay, so that we can get D equal to 4 b cube by u r square. You can use this one. So this is the case of non-rigid rotator. So you will see, due to this non-rigidity, the energy spectrum, you see there is a negative contribution, the centrifugal distortion term. So energy levels will be reduced. So energy bands will be shifted towards left. Now you see, for this one, okay, no, I think this is not the right spectrum to show. So this is the case of the non-rigid rotator, where you can observe a shifting of the energy bands to the lower energy side. So that is the case of non-rigid rotator, and actually that is the most practical case. And obviously the selection rule is delta J equal to plus minus 1. There will not be any change. The selection rule is same everywhere. Okay, so today I will finish up to this part, and because there are several other issues like linear polyatomic type molecules, symmetric top molecules, asymmetric top molecules, and from there we can also focus on the Stark effect and quadruple hyperfine interaction, etc., etc. And also we shall focus on the instrumentation of the microwave spectrum. So today I end up here. So if you have any questions, you are free to ask. If you have any question, you just unmute and you are free to ask. Okay. This one, right? Okay. So suppose this is the HCl molecule. Okay. So this is a hydrogen atom. This is Cl atom. As you know, the charge distribution, there will be delta plus over H and delta minus over Cl. So there will be dipole moment directed from H to Cl. So we are presenting this as dipole. Now, if the molecule rotates about the axis, an axis perpendicular to the bond and perpendicular to this screen, so it will rotate clockwise. Now it will come to this position. The orientation of the dipole change. Now it will again rotate, the direction of the dipole moment change, and due to this dipolar oscillation, an electromagnetic field is generated, and this field will interact with the incident electromagnetic radiation. Okay, and that is how the this rotation leads to the absorption of energy. Okay, and if this interaction is not here, then it will not show any rotational spectrum. So if the molecule has no dipole moment, So this type of rotation does not induce any kind of this dipole oscillation. So it will not interact with the electromagnetic radiation, and it will not show any rotational spectra. Okay, so it's clear now. If it do not have permanent dipole moment, first let me clear two things. If it do not have permanent dipole moment, it will not interact with the electromagnetic field. Do you agree? If the atom do not have any dipole moment, permanent dipole moment, okay, so it will obviously it will not interact with the EM field. And now your question from the basic electrostatics, that if you are saying that if you are applying a field, the dipole may orient at certain angle, right? But that will not true, because whenever you are applying electromagnetic radiation, the field is changing its direction with certain frequency. So the dipole will obviously oscillate. It will cannot have any fixed position or fixed orientation, because the field is changing itself its direction. Okay, is it clear now? Okay. So any more questions? If anybody have any questions, then you can just unmute and ask. Huh? So what is centrifugal force? First tell me. So if there is a centrifugal force, suppose you have a spring and you attach two mass on and you attach two mass on the either side of the spring, right? And you rotate, if you rotate the system about an axis perpendicular to the spring, what will happen? The spring will continue. First tell me what type of field you are applying. First tell me what type of field you are applying. This is an electromagnetic field. That is the electric field oscillating. It's changing its direction. Okay. If you are applying some static electric field, in that case the dipole moment will be induced. That you have learned in electrostatics, right? And this is electromagnetics, where the electric field is oscillating. So there is no scope of static separation of the charges. So there's usually dipole moment is usually not induced in by applying this AC field. Okay, I'll come to that. Obviously, after finishing this rotational spectra, vibrational spectra, and electronic spectra, I'll come to Raman spectra. Okay, that type of vibration is a little bit different from this one. And for information, Raman spectra is also nothing but kind of rotational and vibrational spectra. Nothing new in that. Okay. Any more questions? If you have any more questions, you can free to ask. Eh? No PDF is already no PDF is supplied in the Google Classroom. Actually, all class things all will be given. That is not already given, because I am planning to have some online. The questions will be set in online mode, and you have to answer what they are. So I am the Google form is actually not prepared. Okay, so that's why it's not given. It will be given week by week, and all information, all announcement related to the course, regarding the class timings, everything will be updated in the Google Classroom rather in WhatsApp chat. So all of you are requested to join in the Google Classroom, so that whenever I make any kind of announcement in the classroom, you will have a notification over email. Okay. You can follow the molecular spectroscopy book by Manuel, molecular spectroscopy, atomic and molecular spectroscopy by Rajkumar, modern physics by Arthur Weiser, or physics of atom and molecules by Bransden Joachim. And all, I think, except Rajkumar, I don't know it is not available or it is available or not. Or for all other books, the PDF copy is available in the online, so you can just download it. Because I cannot upload that book in the Google Classroom, that is unauthorized. Okay. Otherwise, I could have uploaded it in the Google Classroom, but that is unauthorized. Any more queries? Peter? Ah. Hmm. Because if you take we have this rotational spectra, if we talk about these basically molecular spectra, mostly we say the molecules mean either this is mostly available in we are considering this liquid and gaseous form, right? So for this kind of fluid which is contained in a container, the space available for this translation motion is quite large compared to the molecular dimension. Suppose the gas is contained in a container which diameter is few centimeters, 5-10 centimeters, whereas the molecular diameter is only few angstrom. So this dimension of the container, that means the translation and length of the translation motion is quite large compared to the molecular dimension. That's why the translation energy is continuous but not discrete. So that will not come into the picture because that will not give any kind of discrete transitions or discrete spectrum. That's why the translational energy spectrum cannot be observed by ordinary emission or absorption spectrum. Okay, is it clear? Any more questions? So okay, I think no more questions are there. So thank you very much, and here we end.